what we really want out of these three pieces of information is the clock time delta t, the time interval delta t over which the motion takes place. Once we have that delta t, we'll be able to go back to the x motion and determine the delta s. So we write the equation that involves initial velocity, displacement, acceleration, and time interval delta t. That equation is delta sy equals v naught y delta t plus 1/2 ay delta t squared. To solve this equation for delta t, we're going to have to bring everything onto one side. We note that we have a delta t squared and a delta t, which makes this a quadratic equation. And to solve a quadratic equation, you bring everything on one side, set it equal to 0, and then use the quadratic formula. Now, some of the details of that are there in your notes, and I'm not going to go over the details, but I simply add a negative delta sy to both sides, and I get 0. And then when I solve for delta t, well, the coefficient of delta t squared is 1/2 ay. That would be the a in the quadratic formula, where you have at squared plus bt plus c. And the quadratic formula then tells you that the solutions are negative b plus or minus the square root of b squared minus 4ac all divided by 2a. The a is going to be this 1/2 ay, the b is going to be your v naught y, the c is going to be your negative delta sy. And we're going to put those into the quadratic formula, and we're going to obtain these solutions. Delta t is negative v naught y plus or minus the square root of v naught squared plus 2ay delta s over ay. All this is very straightforward. We simply plug the quantities in from the equation. Okay, just to recapitulate, here we have our solution for delta t. Let's zoom out a little bit and then examine these solutions. Okay, one of the first things we'll notice is we do have a plus or minus here, and we're going to get two solutions. This is going to require some interpretation, but that interpretation, as you'll see, will be fairly simple. We plug the initial velocity, 2.5 meters per second, into the equation for v naught y. Ay is negative 9.8 meters per second squared, and delta s is negative 10 meters. And then we simply do the simplification. Now, I take a couple of extra steps here, and I'll explain my reasoning in a minute. We can add these terms together, of course. This is all very straightforward. We get this. Now, I could combine the numerator and get two different numbers and divide by the denominator, but instead what I want to do is I want to take the square root of the 202.25 meters per second squared, get about 14.2 meters per second. That's meters squared per second squared, but I get this. And then I'm going to break this into two fractions, 2.5 over 9.8 seconds, which is what we get when we divide this term by the denominator, and 14.2 over 9.8 seconds, which is what we get when we divide this term by the denominator. Of course, there's a plus or minus in here. And we get 0.26 seconds plus or minus 1.43 seconds, which gives us two answers, negative 1.17 seconds and plus 1.69 seconds. Let's just think about what these numbers might mean. The 0.26 seconds came from dividing this term of the numerator by the denominator, and that's really our original y velocity divided by the y acceleration. And what that gives us is the time required to fall. That gives us the time required to reach a velocity of 0. And you can think about why that might be, but it's going to take us 0.26 seconds to reach a velocity of 0. That is, to reach the highest point in the trajectory. And then the 1.43 seconds is the time required to fall from that maximum height. That being obtained from the square root over ay. If we're falling from the maximum height, our initial velocity is 0. And, well, you can work out the details of why that would be the case. Anyhow, we do have this interpretation here. The bottom line, though, is that we end up with these two clock times, which we're going to have to interpret.